How is everyone?
Doing pretty well, Nick. How are you doing?
Doing good too, thanks. So yeah, someone in chat was getting valgrind errors in a init. They shouldn't be coming from a init itself. A init, you're allocating space for a node, setting your sentinel equal to it, setting that sentinel's next field to be null. But I'm gonna guess that there's something else going on in a init, or maybe you had a different variable, or you looked at the node's next field before you set it, or something. Come by office hours, we can definitely look at it. Actually, I can take a quick peek right now. There's nothing in your... There's nothing in your init that should be giving you a valgrind error. So when valgrind gives you errors, it gives you multiple pieces of information. So first thing, so here's some valgrind hints. First thing, always make sure that you compile with the G option, right? That will help valgrind give you specific information where an error is happening, right? So on your GCC, do GCC-G, both to make your objects and your executable, just like you were going to use GDB. And then valgrind will be very specific in its information. Valgrind, like most errors that come out in the compile or the run process, they're usually reverse ordered, right? The first message you see is the one that's actually telling you where the problem occurred. But that will be followed by, you know, if this occurred in my add function, that was called from my main function. And then if it can, it will tell you later on some more information. And I'm going to guess what it's telling you is that the error occurred in add or search or print or something like that. But then later on it's saying that this was a block of memory that was allocated in a init that was called from main. But I don't think the error is actually coming through from a init itself. So try playing with that and see if it helps. Take another look, put on the G switch, and take another look at the valgrind message and see what the first message is that it reports, what program, what file, and what line number. And yeah, it is exactly like a stack because it is a stack, right? It's kind of unwinding the history of how you got to this line that caused a problem, and it's showing you a bit of a stack trace, right? Which is this was called from here and that was called from there and so on and so forth. Okay, yeah, so check the search function. So yeah, you need -G every time that you use GCC if you want to use the debugger. So if you're compiling down to objects, right, you could do something like that. If you're being quick about it, right, from the command line you can just go ahead and do that. Don't do that in the make file because that's not efficient. If you're really being, you know, Fast and Furious. You can, of course, just do that from the command line. Don't do that in the make file either. I think you need the -G when you link. I'm not positive. And maybe you don't need it when you link. Maybe I've just been doing that out of superstition. Doesn't hurt. Alright, cool. Other questions? Issues with PA1, PA2. So hopefully you turned in PA2. If you didn't get it turned in, turn it in before 8 o'clock tomorrow morning. Okay, I'll do another download at 8 o'clock Saturday morning, and you lose some points, but I'll still be able to grade it. I can save myself 3 keystrokes now for the rest of my life because I don't need -G when I link. I didn't know that. Invalid read of size 8 from valgrind. What does this mean? I'm gonna take a stab in the dark and say that somewhere you did a malloc on size of struct node star instead of size of struct node. Or it could be freeing memory and then accessing it. That's true. So again, if you use the G switch, valgrind will generally pin down pretty close to the actual exact line where the error is happening, which may not be where the problem is in your code, right? It might say, you know, well, there's a problem here at line 17 in add.c. But the problem may have been set up, you know, when you did a delete, for example. Maybe you deleted a node you didn't mean to, but it'll help. And if you don't find these, right, you can definitely come by office and we can work through this together with valgrind and look at the code and figure it out from there. Alright, so I'll get linked list 2 graded sometime over the weekend, hopefully before Monday, and then we can talk about general comments on it in Monday's class. Up at 5 a.m. finishing, yeah, I've been there. My worst semester in college, I had an engineering lab class at 9 o'clock in the morning, and I was always up, you know, all night the night before working on it, so I wouldn't sleep. And then I had a database class that night at 9 o'clock, and that was just a bad combo because it's Friday night and you're taking a database course and you've been up, you know, 36 hours plus, so there was a lot of sleeping going on in that class. Accidentally deleted mine at 8, had to rewrite it. Oh no, that's terrible. Yeah, I've been there too. And not to be annoying, right, but use git. Use git if you accidentally delete it. it'll take you, you know, 5 minutes to pull down the clone from GitLab, and you're back in business. And yeah, I've been coding in one form or another for over 40 years, and you know, as recently as 6 months ago, I accidentally wiped out like the whole directory tree of a project I was working on. And I had some of it in Git, but I wasn't actually, like, you know, doing the things I tell you to do, like pushing it frequently and so on. So I actually lost a whole bunch of work in doing that. And it happens, you know. We're all human. Oh no, you deleted during the commit. That's even worse. But if you are committing and it gets deleted, right, you can still go back to earlier versions, even if you wiped everything out and committed the wiped out directory. The older stuff is still around. If it's not on GitLab and you actually like remove the entire directory on your machine, then you know you're out of luck. But if you haven't wiped out, you know, the .git subdirectory, or if you've been pushing it out to the cloud, you can go back to the older stuff. All right, so PA2 is done. We'll post PA3 towards the end of next week. I haven't decided what that's going to be about yet. And we're coming up to the halfway point of the course, right? Next week is week 5. It's a 10-week quarter, so we're moving along quickly, which is awesome. Your midterm is in 2 weeks, so we'll talk more about that next week. But that's coming up. All right, let's look at another application of a stack. So stacks can be used to solve mazes, and we can also use queues to solve mazes. And so I want to look at how we use both of those data structures to run a maze. And it's going to be something that we'll come back to again and again in this course and next course. It's this fundamental concept of searching. So solving a maze is searching for a solution. What are we searching? We're searching all the possible paths that we can take through a maze. So here's a sample maze, and we're starting here. We're trying to get to the end, right? So there's a number of paths we can take. We can start here and we can go left. We can start here and go left and left. We can start here and go right and right, or come here and go left and left, right? And there's this space of all these different paths we can take, and we're basically searching for a path that begins here and ends here. So it's a search problem. And anytime we're doing searching, there's 2 basic approaches that we're going to see again and again. There's the idea of a depth first search, and there's an idea of a breadth first search. And we're going to talk about this more when we talk about trees. But let me just show you, without any explanation, an example of a tree. So if you've already done 215, it's like a graph, but it's got some special characteristics. And let's say this is a tree of possible paths that Mr. Panda can take while trying to get home. So this is from I can't read the name of the URL, but anyway, it's a educational resource, or maybe it's for pandas, you know, to help them out in the real world. So let's say this is a collection of possible paths that we could take, and we're searching for the one that, you know, goes from start to finish. And suppose we can move, you know, from one spot to another by following these lines, but we can't go directly from here to here. So the question is, you know, how should we travel among these possible options so that we cover every possible option? And there's two basic ways to do this. Depth first would say, hey, okay, so we're always going to start up here. It would say, hey, let's go down as far as we can. Go down, 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 deeper and deeper, and hey, let's check this one. All right, if that's not what we're looking for, let's come up one level and then start going down as deeply as we can. All right, here's another one. Let's check that one. Not the one we want? Okay, let's just come up one level and try going deeper again. There's another one. Okay, not the one we want. Let's come up one level. Okay, we'll visit that. Not the one. Come up here, visit that. Come up here. But we can go deeper at this point, so let's go down here and visit that. So it keeps moving down, and it's going to explore all the stuff over here before it ever gets down to any of the stuff over here. So that's depth first. And it's kind of, you know, following things like this. A different approach would be breadth first. And going broad instead of deep would say, hey, let's try this one first, and then let's come down and look at all the things that are one level deeper, and then all the things that are 2 levels deeper, and 3 levels, and 4 levels, and 5 levels. Yeah, kind of like A-star. I think it's kind of fortunate that we like pay bills and go to work, or at least the going to work part, because it lets us also like do other things. All right, so depth first versus breadth first. What does this have to do with Mr. Panda? When you and I solve a maze, what do we probably do? In most cases, we start off and, you know, we look ahead. But supposing we can't look ahead because we're a computer. We start off and we get to a decision point and we say, oh, let's try going here. Nope, that didn't work. So we back up and we come to another point. Let's try going here. Nope, that didn't work. We come here and say, okay, let's go this way. Nope, didn't work. We back up one step and we try something different. Right? So let's say I started off going down here and I came across here and I decided to go down here. That didn't work. I come back and I change that last decision that I made. And I say, okay, let's go straight instead. Let's try going up here. Nope, that didn't work. I come back and I redo the last decision that I made. And I may not go back and try going this way until I fully explored the deepest, the furthest I can possibly go from this current path onward. So I'll try this, no, I'll try this, no, I'll try this, no, I'll try this, hey, that looks good. I'll come up here and try that, no, I'll try that, I'll try that, I'll try that, nope. Now I'll come all the way back and I'll say, well, let's try this. And hey, there we go. So yeah, it's definitely how quickly you solve it is kind of unpredictable, and certainly if you knew the algorithm one was going to use, you could design a maze that would deliberately take them longer rather than being quicker. And by the way, if you really need to solve a maze, usually if you start from the finish, it's a lot quicker to get to the start than starting at the start and getting to the finish. Because usually the multiple options come in this direction, not in that direction. Although this one's pretty good. It's actually got some variations. All right, so how do we do this in a computer? So let's look at a depth first approach to maze solving. So I'll start off, and my rule is going to be when I get to a decision point, I'm going to try going right, I'm going to try going straight, I'm going to try going left, in that order. That's a cool idea, building a maze from both ends in, so that you don't have that pitfall. That's cool. Yeah, well, we didn't want to be too hard on Mr. Panda, I guess. All right, so let's start off here, and I'm not going to worry if I have no decisions to make. So, you know, I've got to go straight here, I've got to go to the left here, but here's a decision point, A. And my algorithm says first try going to the right. Well, that's not an option. Then try going straight, and then try going left. Okay, so I'm going to remember that at branch A, I tried to go straight. And I'm going to go down here until I get to another decision point, B. And at B, I'm going to remember that I'm going to go straight, because I can't go right. Straight's the next option. So I'm going to go here, and here's another decision point, C. Okay, first direction to go is right. So I'm going to remember that at C, I'm going to the right. And I'm going to come down here, and I've got to follow this, and follow this, and follow this. And bang, there's a dead end. Alright, so what do I do now that I've reached a dead end? I made a mistake, right? Somewhere there's something that I should have done differently. Now I could go back and I could change what I did at A or B or C. Usually what we do is we go back to the last decision we made. We go back to C, so we get rid of that, and we say, okay, well, we went to the right, that didn't work. We could go straight, so let's try going straight. So we go straight, here's a branch point D. We'll try going to the right, so we'll make a note of that. We come down here, here's another branch point E. We'll try going to the right, which is over here. We'll try at F, going straight, and that brings us down, and there's a dead end. Alright, go to the last turn that you made, and instead of going straight, let's try going left. So, I guess I should have done right first, but anyway. So we'll try doing this one, and that's a dead end too. Okay, remove that. There's nowhere else we can go from F, so what do? We go back to the last decision we made before that, which was at E, where we decided to go right. Let's try going straight, and that brings us down here. And so on. Yeah, the good old right-hand rule. I'm reading chat right now. Are there strategies involved in partial breath, partial death? Sure. We can switch back and forth between the two approaches. And in an algorithms course, you'll spend a lot of time looking at trees and doing different ways of searching them and pruning them, right? Being able to eliminate an entire subsection of possibilities will help. Had a lot of fun not doing my work in middle school, but drawing mazes, yeah. I can relate. Oh, don't fork a process at each turn. That would be interesting. Difference between an algorithms course and a data structures course. Data structures is looking at how we organize information. So, you know, what's a linked list? It's a way of taking a bunch of data and creating associations between the data that we're storing. So it's not just a pile of stuff. and I want a number, start digging through the pile, right? It's saying, shoes go over here and they get, sorted by color, and shirts come over here and they're sorted by sleeve length, right? And so when you want to find something, there's an algorithm you can use to find it. That's basically what a data structure is doing for us. It's not just about search, but it's in some ways, about search and retrieval. And so those are the things we're studying, right? Lists and stacks and queues and hashes and trees and tries and things like that. And algorithms course really digs into what you do with that information. How do you create these structures? How do you use these structures? And how do you know that those algorithms that you're going to use are correct? So proving, the correctness of our code that traverses a linked list and searches for a piece of data. Looking at order of complexity. How do you prove that this is order log n? And what's the worst case? What's the average case? What's the best case? Those kinds of things. So yeah, data structures is noun, algorithms is verb. That's not a bad way to look at it. So forking a process at each decision point is actually not a bad thing to do in terms of parallelism, right? So if you wanted to do a maze solver in parallel that was very efficient, that's what you would do at each point. You would create another process to explore each of the possible directions. And now the time to solve the maze would be basically on the order of the number of steps from the start to the finish along the winning path. And so that's closer to A star. That's something that I call ants at a picnic, because you start from one point, just farm out in all possible directions. Whoever gets to the finish first, they found the shortest path. This is some version of how slime mold solves mazes also, although I don't think we understand exactly how that works. All right, so what kind of structure is this? Right? What does this kind of scream out? Stack or queue? Definitely a stack. Right? It's a stack because when we have to go back to a previous decision point, which one do we go back to? The one that was most recently the decision that we made. Right, so it has that LIFO structure. And that tends to be how most of us solve mazes, but it turns out we could also do this with a queue. With a queue-based approach, we would start off here, and we'd say, let's go straight, let's go straight, let's go straight. We'd start off here, and we'd go to the right. We'd start off here, and we'd say, let's go to the right first. And we'd follow that and we'd find a dead end. Okay, once we find that dead end, well, okay, we'd start off at C. So we go A, B, C, we'd go to the right, we find a dead end. At that point, what would we do? We'd go back and we'd try a different direction at A. And we'd say, okay, well, what if we went that way? Well, that wouldn't work. So now we try a different direction at B and say, what if we go that way? Well, that wouldn't work. And now we'd say, okay, well, what about C if we go that way? Let's try that. And we get to D, and we'd come down, and we get to E, and we go over, and we go up, and that would give us a wrong, a dead end. And so we'd go back to, the first decision point that we haven't completely exhausted yet, which is D, and we'd say, well, let's try going up. And that doesn't work, and so then we'd come down, and we'd say, okay, well, let's try exploring E again. Well, now in this case, we'd be coming down here before we explored, this path in F. So this feels weird to most of us, to me at least. Stack feels more natural, but queues also work. That actually is breadth first. Where looking for paths by looking at all the short paths first, right? Going back and trying a different option here at point A is saying, let's suppose that there's a path we can get to by coming here, right? It's going to find a shorter path in some way. And if we draw out trees for this, right, you'll see that this is a breadth first. But I don't want to get into trees yet. Yeah, slime molds are a thing. I'll show you a slime mold. I think I'll show you a slime mold. I can't find it right now. Anyway, slime molds. If you take a maze and you put some oats over here and you put slime mold there, it'll branch out and it'll fill all the possible passageways until it finds the oats. But then it does something really cool. It contracts and pulls away from all the paths that didn't lead to the slime mold, and you're left visually. You can look and you can see the solution to the maze because it's gone down to just making a path from the start to the finish where the food source was. So yeah, so someone says depth first seems like on average it would be faster, but worst case would be to explore the entire maze. Breadth first would always reach the end in a set amount of steps, but would explore more of the maze on average. Something like that, yeah. It's possible that either approach could take a really long time depending on how your maze is set up. I think if you made a maze that was hard to do with a breadth first, I think it would look really funny. And I suspect if you tried to tackle that with a depth first, it would be a really easy maze. Because it could be something... I'm terrible at drawing mazes. Right, I think you could make something like this, and if your search pattern was right, straight, left, I think this would take you a really long time to solve, because you would keep, like, trying all of this. But I don't know. So that's the case where we can use stacks or queues, and we'll see that with binary trees. And binary trees, we will be interested in both search patterns, breadth first and depth first. All right, let me show you one other application of stacks. Actually, no, I'm not going to do that. You can make a calculator using a stack, but I may do this for part of a future programming project, in which case we'll go through the details of it. If not, if you want to see it, you can watch it in the previous section's video, stack-based calculator. But let me go on to talking about hashes, because that's going to be our next topic. Oh, interesting. Yeah, and a right hand versus left hand does seem different. And most of us, we tend to go straight, I think, before we try left or right. But this one was easier to trip up by doing right, straight, left. And we don't always use the same rule. But humans, we look ahead, right? So we look at this maze, and it's pretty clear we don't want to try that or that or that, and it's probably pretty clear at this point we don't want to go there. So we don't actually move our finger and try all of those. We keep our finger here and we look and say, nope, that's not going to work. And we come down here, and then at this point we kind of look at that and say, nope, and so we go down like that. All right, so let's talk about hashes. So hashes are like most of this, about storing and retrieving information, and trying to do this efficiently. But they're more than that. Hashes tie into security issues. They tie into, you know, if you want to tag your music, you've got a audio file and you want to figure out, you know, artist and album and things like that. And so you want to go out to a database like Picard and get that track information, right? How do you search a huge database using a sample of sound, right? That's something we can do with a hash function. If you download a file and you want to know, is this the actual executable file, or has this been modified to have, you know, some kind of malicious code inside, that's a hashing function. And one of the more interesting aspects of hashing is it seems to be related in some way to cognition, to how our minds seem to work, how we store and retrieve information, which is linked in with how we think. Right? It's not just, you know, we have a big array of knowledge and we go in and we pull knowledge out when we need it. But the way that all of that stuff in our heads is organized is somehow linked in with how we actually think, how we conceptualize, how we process. And so this is, you know, potentially a really cool topic. So let me give you an example. Let's suppose we're making a database. Okay, doesn't have to be organized, but we're making a collection of data. And let's say we want a database of office numbers. So here's Nick, and I don't know my office number anymore. It's like your phone number, you never have to call yourself. So, but let's say my office is 105. Or 109. Let's say Izad is 113. Well, we'll make him 111 because I typoed. Let's say Tina is 103. And Carol is 105. And Scott is 107. And I'll do a shout out here because someone mentioned missing Scott last time. We got talking about that. Scott's doing a machine learning class in spring, as far as I know, CSE222B. I think it's 2 credits. If you're looking for an extra 2 credits, or if you have space and you want to take a machine learning class, check that out. I believe that's being offered in spring. And he offered this last spring for the first time, and students seem to really like it. So, yeah, so someone says it was an interesting class. So check that out. Machine learning CSE222B. No, I never have my ringer on, so calling my phone when I lose it doesn't help. So, but I never use my phone anywhere. It's always sitting over there on the table, plugged in. So that's not an issue. All right, so we have a bunch of names, we have a bunch of offices, right? And we want to store this information so I can say, hey, what's Izad's office number? And my software will say his office number is 101. All right, so so how do we do this? Well, you know, we could store this in an array. And, you know, someone wants to find Scott's office. Is this Scott? Is this? Is this? Is this? Oh, there's Scott. What's the office? 107. Okay. Order n, worst case. We can make a sorted array and we can play high-low. Start in the middle and keep dividing the list of possible locations in half. That comes down to order log n. So that's a lot better. But our ideal, you know, for search is always order 1. We would like a way to search this information so that as we add more and more information, it doesn't take us longer and longer. The search time stays the same. And you know, with an array, sorted or unsorted, with a linked list, even with a binary tree, the more data we have, the longer it's going to take on average to find a piece of data. So here's an idea. Instead of having one array, make yourself 26 arrays. And I'll store Nick in the array that's corresponds to N. I'll store Izad in the I array. I'll store Carol in this third array for C, and so on. And now if I want to find a name, I can look at the first letter of the name. That tells me which of my 26 arrays that name is stored in. Now I have to search a much shorter array. Because if I have, you know, 26,000 names, well, each of these arrays is probably only about 1,000 names. That's going to be faster. Yeah, I bet you see where it's going. So yeah, this will be an associative array. Alright, so doing this works great, but you know, everybody whose name starts with the same letter gets stored in the same array. And if you've got, you know, 26 gazillion names in this database, each of these arrays is a gazillion entries. It's going to take you a long time, because it's still order n. So how do we improve on that? More arrays. Let's use the first 2 letters of the person's name. Let's make an array AA, an array AB, down to an array AZ, and then BA, down to BZ, all the way down to ZZ. Alright, we have a lot of arrays. How many arrays do we have? We have 26 squared arrays. But by just looking at the first 2 letters of the person's name, we'll identify one of these 26 squared arrays that name could be contained in, and all the names in here are names that start with BA. Well, there's probably not that many, right? In fact, on average, there's, you know, our entire universe of names divided by 26 squared. So these arrays are going to be shorter to search. But, you know, a gazillion pieces of data, that's still a lot of stuff in each array. So how do we make this even better? Without thinking too hard. Add more arrays. Let's make 26 cubed arrays, where each array corresponds to a particular first 3 letters of the name. Well, now we're really going to be in good shape now, because unless 2 people have the same first 3 letters in their name, you know. But, you know, if we're storing a name, which is, you know, a first name and a last name, everybody with the first name, Bob, is going to end up in the same array if we're doing this first name, last name. If we're doing last name, first name, everybody whose last name starts with MAC, like Mac, you know, or me, is going to end up in the same array. We don't have to do any searching though to find one of these arrays. So suppose we just had 26 arrays, right? I'm going to store all of these in another array. So I'm going to have a two-dimensional array. This is going to be element 0, element 1, element 2, element 25. So how do I figure out which array to search? Take the first character of the name, and let's suppose, you know, A equals 0, B equals 1, Z equals 25. So adjust your ASCII code, right? Take the first element, first letter of the name. That tells us which array to search. Well, if we have two element arrays, right? This is name 0. This is name 1. We can write a pretty simple formula for this. The index is just name bracket 0 times 26 plus name bracket 1. So BA, B is a 1, A is a 0. BA would be stored at the array whose index is 26 plus 0. So that would be this one right here. And if you have 3 of these, right, the index, you know, it's name 0 times 26 squared plus name 1 times 26 plus name 2. The specifics aren't important, right? But we can write a pretty simple mathematical function which says, hey, give me the first 3 letters of the name, I'll tell you which of these 26 cubed arrays to search in. So now imagine that max name length is 20 characters. So if I make a humongous array containing 26 to the 20th subarrays and a little more complex formula which takes a name and by looking at each letter tells me exactly the index of the array that contains that name, I get a name, it gives me, you know, look at row 17, skrillion, and 12. I go to that array, there's the name, there's the office number. This is order 1. So this function is called a hash function. And this data structure is called a hash. And yeah, it's also called an associative array. And the basic idea is the thing that you're looking for tells you where to find it. Which is marvelous, right? I want to find, you know, this piece of information. Well, if I just look at the name of the thing I'm looking for, encoded in that is the information about where to find it. So I use that hash function to, you know, find that location from the name, and bang, there it is. That's the sense in which it gets to be order 1. We're not actually searching. We're letting the thing we're searching for tell us where it is. Okay, these are kind of magical. Okay, if they feel like you're getting something for nothing, yeah, you're understanding it. All right, so we'll dig a lot further into hashes Monday and next week. We'll talk about linked list 2 and wrap that up on Monday also. I will see you in 2:15 if you're in there. If not, have a good weekend, and I will see you next time.